All right, this is a first lecture on natural selection and population genetics. This comes out of chapter 3 in your textbook, but I'd like to provide a little bit more background around it. All right, so we know that there are different kinds of variation. We often care about the phenotypic variation we observe because it contributes to fitness variation, difference in survival and fecundity. This is driven in part by genotypic variation and environmental variation. This is a framework we've understood since the great work of R.A. Fisher, the British population geneticist and the founder of modern statistics. All right, so we can look at differences in mosquitoes that carry, this is Culex pipens, carries, I believe, malaria, across different countries and look at variation at nucleotide positions in those mosquitoes. The kinds of variation we observe may be due to differences in the genetic system and the type of selection. We are going to start with the simplest forms of selection that assume a diploid organism, single biallelic variation, and random mating among individuals. And we're not going to look at all the other factors such as drift, migration, mutation, inbreeding that can affect selection. We're going to assume it's identical between the sexes, that it's through differences in viability, and it's constant in space and time. Each and every one of the factors listed here in real populations happens to co-vary with the strength of selection. Selection is hardly ever uniform. But for the sake of modeling it, we're going to start with this and then increasingly complicate it by later adding in other factors. So the general framework that we use, coming from Fisher and from Haldane, is to look at fitness as a relative measure, where the total fitness or the highest fitness we set to 1, and we can look at the fitness of each genotype in relation to it. And we use these subscripts for reasons that are not important. We use W as a common subscript for fitness. And we're going to use 1, 1, 1, 2, or 2, 2 to indicate which genotype it is. So 1, 1 is the big A, or A1, A1 homozygote. And W1, 2 is the fitness of the heterozygote. And we can use the Hardy-Weinberg frequencies to indicate the frequency before a bout of selection. So the subscript 0 simply indicates time of 0. And then we multiply the relative fitness, the W, by the initial frequency. And that gives us the frequency after selection. This W with the bar over it is the mean fitness of the population. Okay, so it's basically just the sum of all fitnesses. Okay, so this isn't complicated, but the notation certainly confuses many students. All right, so different kinds of selection that favor one genotype or another give different outcomes. Selection for A2 or for A1 will lead to an increase in those genotypes. Selection for the heterozygote, where the heterozygote has an advantage, leads to a stable polymorphism, where both alleles should persist in the population. Heterozygote disadvantage happens to be pretty unrare, and it's also unstable, and it's usually going to lead to one allele or the other going to fixation. All right, so we can look at general fitnesses in a couple of ways, where there's a recessive lethal. That means that one genotype has, one homozygous genotype has a relative fitness of 0. It simply dies. There can be detrimental alleles that have a fitness lower than the other one. And this can be recessive or additive. When it's recessive, that lower fitness only occurs in the homozygotes. If it's additive, depending on how many of the weaker allele are had, an individual does less well. So the heterozygote is less fit than the homozygote of the other allele, but still does better than the homozygote of the disadvantageous allele. There can be different forms of dominance that look a little bit different. So we can use HS to indicate the fitness of the heterozygote, which may be higher, and distinguish purifying selection that removes one allele versus positive selection. And then heterozygote advantage, where both homozygotes are selected against, and disadvantage, where the heterozygote is disfavored relative to both homozygotes. All right, so we can graph this over time to look at expected versus observed frequencies, and in many short-lived organisms, we can perform these experiments. We can also model what the frequency should be at different times depending on the strength of selection and the starting frequency. So your book has a section on this that's worth pursuing more carefully. And we can predict stable equilibria where populations should end up after selection over time. All right, so this is our general formula for looking at frequency after selection. It's worth noting that recessive, additive, and dominant alleles go to fixation differently when they're favored. Dominant alleles will generally increase in frequency quite rapidly, this dotted line here, but they rarely go completely to fixation because a recessive disadvantageous allele can lurk in the heterozygous state in a large population. Additive alleles go to fixation nearly as quickly, and unlike dominant alleles, they will go completely to fixation because there's still selection against the other allele in the heterozygous state. It can't hide as a recessive. Recessive alleles behave quite differently. When they are favored, they take a long time to go to fixation because they're mostly in the heterozygous phase until they're fairly common in a population. And thus, even if it's favored, a recessive allele at low frequency doesn't tend to increase in frequency very much until perhaps due to drift as much as selection, it increases in frequency. I'd like to stop there. There'll be more lectures that follow up on these themes of selection.